The broadcast is now starting. All attendees are in listen-only mode.
Good afternoon. This is Alan Roberson. I'm Executive Director at the Association of State Drinking Water Administrators, and I'd like to welcome you to this afternoon's webinar. Today we have a real treat. We're going to hear a presentation on perfluorinated compounds from Detlef Knappe. Dr. Knappe is a professor at North Carolina State University. I've worked with Detlef for about at least a decade on a variety of drinking water issues. He's been at NC State for 21 years now. So take it away, Detlef.
Very good, thank you, Alan. So this is Detlef Knappe. I'm going to talk a little bit about legacy and emerging perfluorinated compounds, and the official name for this class of compounds is per and polyfluoroalkyl substances, which is also abbreviated PFASs. And we've been studying these compounds for a number of years now in surface water systems in North Carolina. And what I want to talk about today is their impacts on both small and large systems in a particular river basin here in North Carolina. This work has been a collaboration between NC State University and the US EPA. Andrew Lindstrom and Mark Streiner are two researchers with NERL and EPA here in Research Triangle Park. And Mei Sun, Elisa Arevalo, and Leanne Dudley were all students. So next slide. So PFASs, by definition, are compounds that, well, if we use the word perfluoroalkyl substances are compounds in which all carbon-hydrogen bonds are replaced by carbon-fluorine bonds. Hit the down arrow. And so here we have a one important representative of PFASs. This is the class of perfluorocarboxylic acid. So these are compounds that have a fully carbon backbone, and at the end they have a COOH or carboxylic acid group. And if you hit the down arrow again, I'm going to show here the structure for PFOA, which has been a well-studied compound, is sometimes also called C8, and the structure is shown here. Hit the down arrow again. Then we have here a structure for the perfluorosulfonic acid. So these are compounds where you have a fully fluorinated bone and then a sulfonic acid group. And the most well-studied compound, if you hit the down arrow again, is the perfluorooctane sulfonate, or PFAS, which is an important ingredient in older firefighting foams. And that structure is shown here. Both the carboxylic acids and sulfonic acids are strong acids, and therefore these compounds occur as anions in water. So you have a COO minus group or an SO3 minus group. Next slide. So if we think about PFAS in the current way of thinking about their production, is we classify PFAS according to long chain and short chain. And long chain compounds are the ones that are being phased. That means they're no longer produced in the United States, but are produced in other countries around the world, for example, China. And so by definition, then, for the carboxylic acids, these long chains are the ones with fluorinated carbons or more. So that's PFOA and longer. So 8 carbons in total and higher. For the sulfonic acids, it's for 6 perfluorinated carbons and higher. So it's for the hexane sulfonate and higher. So these are the compounds that more readily bioaccumulate in the human body and also in other aquatic and wildlife. And for that reason, they are being phased out and are being replaced by either short chain PFASs. So these would be compounds where the N is less than what I'm showing here. And also fluorinated alternatives, which I'll talk about later. So next slide. So the PFASs are of concern in large part at these very low levels because they bioaccumulate, and our bodies recycle these compounds and eliminate them only very poorly. So as a result, PFOA, for example, has a half-life of almost 4 years in the human body, and PFAS greater than 5 years. In contrast, shorter chain compounds like the PFBs are eliminated more readily from the body, but still the half-life in this case would be 4 months. Some of the photos here, the Scotchgard, I showed that because up till the early 2000s, Scotchgard was the active ingredient in it was PFOS, the 8-carbon compound, and then it was replaced by the 4-carbon butane sulfonate, and now it's being replaced again by another compound. And then the microwave popcorn bag I'm showing because the microwave popcorn bags are also coated with fluorochemicals, and they have been a source of PFOA and are currently probably a source of emerging PFASs. One of the challenges with toxicity studies is that most of the data that assesses toxicity comes from animal models like mice and rats, and the bioelimination of PFASs in rats and mice is much more rapid in the human body, and that adds uncertainty to how well we can assess the toxicity of these chemicals. The next slide. So as a result of the toxicity and concerns, EPA in May of last year issued a health advisory level for PFAS and PFOA, or C8, that states that the sum concentration of those two compounds shouldn't exceed 70 nanograms per liter in drinking water. And this advisory is meant to be protective of chronic exposure. So that suggests that a lifetime exposure with PFAS and C8 at this level would be considered acceptable. Some states have somewhat more stringent standards or guidelines. For example, in New Jersey, the guidance level for C8 is 40 nanograms per liter, and there are sometimes more stringent guidelines than the EPA health advisory level. Next slide. So one question that EPA wondered, and many others also, is how much are PFAS a concern in US drinking water? And as part of the unregulated contaminant monitoring rule, EPA included 6 PFASs that are shown in this table. We have for the carboxylic acids, the 7, 8, and 9 carbon compounds, and for the sulfonic acids, we have the 4, 6, and 8 carbon compounds. And I'm showing in this table also the method reporting limits that were used for the UCMR3. This was through EPA method 537. And these reporting limits are somewhat higher than what the method can actually do. And so one of the challenges with this data set is that if you look at the reporting limit for C8 and for PFAS, if you add that up, that's 60 nanogram per liter, which is very close to the 70 nanogram per liter guideline. So there is some uncertainty in terms of how fully the UCMR3 data set really represents the occurrence and potential for concern of PFASs. The other aspect of the UCMR3 is that this data set is only collected by public water systems serving greater than 10,000 people. So there's very little data for small systems. Next slide. So the most recent UCMR3 data release was in January of this year. And for the PFASs, this data set contained information from 36,000 plus samples, almost 37,000, that were collected from almost 5,000 public water systems. And if we look in aggregate, PFASs were detected in only 599 samples, which is 1.6% of the total. And so that at first glance looks like it may not be such a big problem if we think about this as a nationwide issue. However, if we look at the data from a public water systems perspective, then 4% of the systems had at least one PFASs, so that's slightly more significant. And then, another question one can ask is are PFASs primarily a surface or groundwater problem? And nationwide, PFASs are primarily a groundwater problem, with almost 3/4 of the samples, actually more than 3/4 of the samples coming from groundwater systems. If you look at individual PFASs, the ones that are most prevalent are PFOA or C8 at 1% of all samples, and PFAS at 0.8%. And then next were the heptanoic acid and the hexane sulfonate. And the C9 and the butane sulfonate were only detected in a very few systems. And I'm showing here locations where some of the highest concentrations were. So next slide. If we from 151 public water systems, and here, PFASs were detected at a higher rate, about 3% of all samples and 13% of the public water systems. So certainly a larger percentage of public water systems are affected. Carolina, and also what's different relative to the nationwide picture is that almost 80% of the hits were in systems that derive their drinking water from surface water. So I guess the point here being is, we shouldn't just look at the nationwide data, but we should drill down a little bit further and see, what are the more localized effects of PFASs in individual states or even regions within a state. So next slide. So in this slide, maybe hit the down arrow one more time as an animation. In this slide, I'm showing a map that was published in a 2016 ESNT Letters paper. And in blue are regions in the country where the PFAS levels, PFAS and the 70 nanogram per liter health advisory level. And so the estimate from this study was that at least 6 million US residents currently drink water that has PFAS and PFOA levels that meet the 70 nanogram per liter health advisory level. And so you can see there are hotspots around the country, whereas there are other areas that are not affected by these compounds. Next slide. So one thing that was of interest to our research team was, are the UCMR3 data sufficient to really paint a complete picture of PFAS occurrence in drinking water? So next slide. And so this is a figure from a paper that appeared earlier this year in Environmental Science and Technology called The Never-Ending Story of PFASs. I recommend that as a good source of information. What this figure really illustrates is how complex the field of PFAS is. If you look at the top two groupings, there are the PFCAs and PFSAs. Those are the carboxylic and sulfonic acids, many of which I talked about, and those are the ones for which we have, in general, more information how well we can remove them through water treatment processes. But what's also shown here is there's a large number of additional PFASs that are on the market, and those are very poorly studied. So if you hit the down arrow, maybe once or twice, maybe start once. Sometimes the response is a little slow. I guess there's a group called PFECAs, PFESAs. I try to highlight that. That is a group of perfluorinated ethers that contain substances that are replacement chemistries for the traditional carboxylic and sulfonic acids. And we also study, there we go, the other class of compounds are the polyethers. These are compounds that have multiple ether groups in them. And so that becomes a new challenge now, because we lack standard methods for many of these compounds, and commercial labs just very recently added methods, for example, for GenX and Adona, which are two of the perfluoroether carboxylic acids. So if we go to the next slide. So Mark Streiner, who works at EPA, was the lead author on a paper that came out 2 years ago that showed the occurrence of these perfluoroether carboxylic acids in the Cape Fear River of North Carolina. And what you can see here is a series of compounds that differ by additional CF2 groups. But what's common to all of these compounds is that they have one ether linkage. So that's one oxygen functional group that is interspersed into the fluorinated carbon groups. And so towards the bottom there, we have Gen X labeled. So Gen X has been in the news of late. Gen X is a 6-carbon perfluorinated ether, and it is a replacement compound for PFOA. So PFOA was a surfactant that was used to make materials like Teflon or Gore-Tex, for example. And since the phase out of PFOA, Gen X has been that replacement surfactant, and that structure is shown here. Some of these other ethers occur with Gen X in this particular river, and we think these are byproducts of a manufacturing process rather than a commercial product. Next slide. So here we have another series of ethers, second series of ethers, and here the repeating functional group is a CF2O group. So we have two, with each compound we add an additional ether group. So at the bottom we have a 3-carbon monoether, then we have the next one up is a 4-carbon diether, and so on. So these compounds also occurred at quite elevated levels in this river. And again, these are compounds for which we lack really every information so far. We don't have analytical standards for them. We don't have any toxicity information on them. But the structures of these chemicals was puzzled out through high-resolution mass spectrometry. And next slide. So I'm going to talk about a case study here for the Cape Fear River Basin of North Carolina. Next. So here's a little geography lesson. So the US map shows North Carolina, and then the North Carolina map shows where the Cape Fear River Basin is located. The Cape Fear River Basin is the largest watershed that's entirely contained within the state of North Carolina, and it supplies about 1.5 million North Carolinians with drinking water. And the larger map shows the actual watershed, and we studied drinking water in 3 communities that are labeled A, B, and C here. Community A is a small system located on the Haw River, and it's upstream of a fluorochemical manufacturer, but it's downstream of a number of larger cities that discharge their wastewater into the Haw River or its tributaries. And Community B is also upstream of a fluorochemical manufacturer and downstream of many tributaries. So at that point, quite a bit of dilution of the upstream wastewater would have occurred. And then in Community, a fluorochemical manufacturer, and we studied the effectiveness of their water treatment processes for fluorochemical removal. We also took a surface water sample just downstream of this PFAS manufacturing plant, and we conducted some adsorption studies particular water. So this one had slightly higher levels of PFASs than what you would have seen at community C. The next slide. So maybe very quickly, we sampled in 1 liter HDPE bottles. We did not add a preservative. We stored at room temperature and analyzed these samples within 7 days. But we also did a holding study that showed that this sampling approach, even after 70 days of storage, showed no changes in PFAS concentrations. Next slide. Our analytical method for the majority of the study was a large volume direct injection method. We injected 900 microliters into the C system that allowed us to process a large number of samples. This was an isotope dilution method, so we quantified all of the PFASs against their mass labeled analogs whenever possible. And our calibration curve ranged from 10 to 750 nanograms per liter. And our limit of quantitation with this approach was generally 10 nanograms per liter, with the exception of C10 and PFAS, which had MRLs of 25 nanograms per liter. So next slide. So here, you can see results for daily composited samples that were collected at the intakes of each of these communities, community A being the most upstream, community C the most downstream. N represents the number of composite samples that we collected. And what you can see for community A is that we have a mix of all of the traditional analyzed carboxylic acids and sulfonic acids. The total PFAS concentration on average in this particular water source was around 350 nanograms per liter. And on approximately half of the days that we sampled, the PFAS and PFOA concentrations in this particular drinking water source exceeded the health advisory level of 70 nanograms per liter. To us that, with the principal upstream water discharges, that we were still seeing relatively high levels of PFOA and PFAS in this drinking water source. In red is Gen X, and what you see here is for community A and also for community B. The Gen X did not occur. If we look at community B, they had a lower number of PFASs that were detectable in their water, primarily because these PFASs out by tributaries that were essentially PFAS free. If we then go on to community C, we see only the butanoic and pentanoic acid as the more traditionally analyzed compounds, but then we see a large red bar, which is the present that indicates the presence of Gen X. In this particular case, the average concentration of Gen X for 35 samples was 630 nanograms per liter. The maximum concentration over this sampling period was 4,500 nanograms per liter. Next slide. This just shows the structure of Gen X. And here, in this particular figure, I'm showing a very similar bar graph summarizing the concentration of the traditionally studied PFASs plus Gen X throughout this treatment plan. And this is a treatment plan that employs advanced treatment processes. It uses both raw and settled water ozonation. It uses a GAC biofilter following ozonation, and it also uses medium pressure UV and free chlorine for disinfection. And what this figure essentially shows is there was no change from the raw to the finished water. Neither Gen X nor the traditionally studied compounds really were altered or removed by the oxidation and biofiltration and conventional treatment processes that are used at this particular plant. I think you need to hit the arrow times. I embedded in here the treatment conditions, but so you can see roughly the well, you can see the total organic carbon and ozone concentrations, and if you hit the arrow one more time, you know, the medium pressure UV dose and the free available chlorine concentration and contact time. So this essentially illustrates that, you know, fairly harsh treatment conditions have no impact also on this Gen X compound, which was thought perhaps to be somewhat more labile than the traditionally studied compounds. Next slide. So in this figure, the red bar from the previous graph is in this oval dashed box towards the left of the graph. So you can see that Gen X, which we also call propoxypropanoic acid, which is that other abbreviation. Gen X, which had a large red bar in the previous graph, is almost barely visible here. And instead we see large responses on our mass spec for other fluorochemicals. And if you hit the down arrow once, we see the structure for the compound highlighted in green. So this is a 3-carbon carboxylic acid. And if you hit the arrow again, you see for the gray bar, this diether hexanoic acid. And so there are a couple of important points here. One, Gen X, which got a lot of attention as of late, was actually a relatively small percentage of the total PFASs that are present in this water, and that we need, you know, better methods, and we need standards for compounds such as the other ethers that are shown in this particular graph. And what this also illustrates is that the same advanced and conventional treatment processes had no impact on the removal of these other perfluoroether carboxylic acids in this water. So high concentrations of emerging perfluoroether carboxylic acids that could not get removed. Next slide. So these data became public knowledge in June of this year, when the newspaper, the local newspaper in Community C, picked up the story, and there was a big public backlash. And as a result of the pushback of local officials and also our DEQ, the fluorochemical manufacturer, Chemours in this case, agreed to stop the discharge of Gen X into the Cape Fear River. And this figure shows the data that have been collected since that promise, and so we can see that the Gen X levels indeed dropped from the 600 to 700 nanogram per liter range. Here I'm showing raw water in red and finished water in blue for the community sea water treatment plant. And North Carolina also very quickly, within a period of about 5 weeks, established a health goal of Gen X, which is at 140 nanograms per liter. And so we can see that the health goal was met after a number of modifications were made. Several places within this manufacturing plant were found where Gen X actually entered the water and ended up in the discharge. The other factor that comes into play here is that this manufacturer doesn't run the processes 24/7 year-round, so the processes sometimes stop, and as a result, we would expect also that the discharge into the water might stop periodically. So one of the key points that I want to make in this particular slide is that it's very challenging with just a few graph samples, for example, quarterly sampling or even monthly sampling, to have a representative picture of what's going on with respect to industrial discharges, which can often be episodic in nature. Next slide. And one more, so I was curious about activated carbon, of course, since that's been a focus in my group. Here we tested a thermally activated wood-based carbon, maybe here a couple of times. This carbon was evaluated in a Water Research Foundation study that we conducted a couple years back, and was quite effective for PFAS removal. And it's, well, maybe hit the arrow a couple of times. So, maybe somewhat drinking water relevant carbon doses, but at the very high end, we just wanted to demonstrate whether carbon has a chance for some of these compounds. And so we conducted batch tests for 60 minutes of contact, next arrow. And we did this in Cape Fear River water that actually has quite a high TOC, in this case 9 milligrams per liter. Next slide. So in this figure, this is kind of a busy one. You see PFAS removal on the y-axis, so percent removal. And then I grouped compounds by chemical class. So on the left, we have the carboxylic acids. Then the next group is the monoether carboxylic acids. And then we have the multi-ether carboxylic acids. And then on the very right, the sulfonic acids. And within each group, the compounds are ordered from left being the shortest chain to right being the longest chain. And so you can see that our ability to remove these compounds by activated carbon increases as chain length increases. I also drew a horizontal line at 20%. The variability of the mass spectrometer is somewhere in minus 20% range. So any data that fall below 20%, I would say statistically means there is no removal. And so we see is that short chain compounds like PFBA or PF pentanoic acid are poorly removed. And if we look at the monoether carboxylic acids, I'm showing here a 3, 4, and well, actually 4, 5, and 6 carbon ether, the 6 carbon one being Gen X. Also PFPROPRA, sorry for this long alphabet soup here. But Gen X was barely removed once we added 60 or 100 milligrams per liter powdered activated carbon into this water. So very challenging to remove that particular chemical. We also, for the multi-ether acids, we first 2 at pretty high concentrations. The first one was not removed at all. The second one barely at very high doses. You know, contrast that with PFOA and PFOS, which are much more readily removable by activated carbon. Next slide. Maybe just hit through a couple arrows so we get done. And maybe hit the arrow again, likely twice. Yeah, one more time. There you go. So here I'm showing removable compounds. PFOA was readily removable by activated carbon. So this graph shows that as chain length goes up, we can absorb perfluoro compounds more readily. And if we look at PFOA versus Gen X, you know, PFOA was much more readily removed than Gen X can be removed with activated carbon. If we go to shorter chains, it's almost impossible to remove them from this particular water. Next slide. Getting close to the end here. You know, we also tracked Gen X removal in a was affected by this discharge from the Kimura facility, and this particular facility had activated carbon in place. This was a reactivated F300 GAC, and this carbon was in place for about 3 months when we started collecting these data. And you know, for this particular plant, they're operating GAC absorbers in parallel. The overall Gen X removal at this particular plant was only 30% using their treatment approach. We're still digging into this data a little bit more. For the carbon that was 3 months old, the removal was somewhat better. But the other thing that we see here is there's a chance that when we have Gen X levels that fluctuate greatly, as illustrated by the raw water concentrations, that there actually may be also desorption occurring if a period of high concentrations is followed by a period of low concentrations. So that's a challenge if we have a surface water where you have highly variable inflows. Next slide. This is just a summary. So legacy compounds were dominant in the upstream river reaches of this watershed. The PFOA and PFAS were still a concern on about half of the sampling days that we were looking at. But once we went downstream of this chemical manufacture, this new class of fluoroether carboxylic acids began to dominate, and they're very difficult to remove by oxidative and conventional and biological processes. And activated carbon really appears to be only effective for the longer chain PFASs, especially if we're dealing with surface water where TOC levels are much higher than in most groundwaters. That's the story. I have just an acknowledgement slide and a slide for questions, but in the interest of time, I think we can open it up for questions now.
Thanks, Detlef. That was a fascinating presentation. I got to admit, I saw this at the EPA Drinking Water Workshop in August and didn't really pick up on that new acronym, PFMOA. And so it just shows the concerns about these new and emerging compounds. So I appreciate seeing this a second time and developing a slightly better understanding of some of the details. Just to let everyone know, we've got Detlef here for maybe another 15 or 20 minutes. We can take a few questions. This webinar will be archived on the ASTO website under events. So again, if you want to go back and take a look at it, then that's one opportunity, or some of your colleagues could make it. So I have a question from Pete. Looks like, clearly UV was tried in that one slide, but did you look at any advanced oxidation? For example, UV and hydrogen peroxide?
Right. We have not, but we know that in this particular plant, ozone is added. They generate a substantial amount of hydroxyl radicals. We know that because in this water is also 1,4-dioxane, and we use 1,4-dioxane as a hydroxyl radical probe. And so all indications are that hydroxyl radical is not effective for the oxidation of GenX and the other ethers. So while we have not directly looked at against oxidation processes or the potential for photolysis at high UV doses, which has been reported to a very, very limited extent at very, very high doses for the traditional PFASs, we feel that AOP is not an option for the legacy PFASs or these ether carboxylic and also sulfonic acids that are present in this water.
So I have one question on my own, going back to this PFMOAA. So it sounded like you don't have a standard for that. So you're just basically using your expert knowledge to determine what the structure might be, or is there any chance of standards being developed in the near future, or how do you as a researcher work with on development of standards so that you can specifically measure this concentration of that compound?
Right. So that's a major effort at EPA right now to synthesize these compounds as standards. That's not only important to accurately determine the concentrations in the water, but right now there are no toxicity studies on these compounds. So we also need these compounds to study their toxicity.
And is that particular compound, the only reason I'm zeroing on that a little bit, Detlef, is the size of that bar in relation to GenX on that one bar chart that you had. Is it a manufactured, or is it more of a manufactured byproduct, or do you know enough about the process to know kind of where it's coming from? Because again, that was a new one for me in seeing the slide deck the second time.
It co-occurs with GenX, and our best guess is that it is a byproduct. And I should point out something important here. The GenX that we're seeing in the river actually is also a byproduct. At this particular Chemours facility, there are two production lines. One production line makes GenX as a commercial product, which is actually an ammonium salt. The EPA consent order stipulates that 99% of the GenX has to be captured at the plant and also by any user of GenX downstream at another industry. So we were initially curious, where is GenX coming from that we're finding in the river? And in this particular case, there's a second production line at this plant that makes monomers for fluoropolymers. And the Gen X is a byproduct in that production line. And if you look at the EPA consent order, it excluded byproducts from the overall agreement. So while the company captured Gen X wastewater from their commercial product production line, they did not when it was a byproduct in the other production line. And we think that in this other production line, along with Gen X, all of these other ether carboxylic acids were produced as byproducts as well.
Interesting. It almost requires you to understand the production facilities chemistry as well as the chemistry in the environment, plus going through water treatment. So got another question from Mark, and it may be a couple compounds that I'm not familiar with, but the question is, any speculation if Nafion BP1 or BP2 will be removed by granular activated carbon?
Yes, so we have some brand new data on that, and the indications are yes. The two Nafion compounds, 7 carbon ether sulfonic acids that have a pretty high molecular weight, somewhere between PFOA and PFOS. And the indications are those two are removed quite well by activated carbon.
And then one question kind of related to that, going back to Pete, is that, okay, let's assume that someone has carbon and takes out the two Nafion compounds, the longer chain compounds, then can you regenerate the carbon? And in my head, then what happens with those compounds? Are they destroyed through the regeneration process to high temperatures, or are we going to break these down into a bunch of smaller ones? It's kind of, you know, can the carbon get regenerated? And if it does, then anything comes off that?
Yeah, I think that's still a somewhat unanswered question. These compounds are thermally very stable. And so if we look at regeneration temperatures, it's unclear to me that we know whether we actually break down all of the PFASs that may have absorbed on this carbon. Now, that would have to be studied pretty carefully, because PFAS in these systems is primarily a function of how much background organic matter absorbs on activated carbon, and the background organic matter gets burned off during regeneration. So once you bring this regenerated carbon back, I would predict it would PFAS like the Nafion compounds, or PFAS or PFOA. What would be interesting to see is, would any PFAS leach off of that regenerated product? You know, I think that that's something that needs to be looked at.
It's fascinating. Again, I'm not a carbon expert. I did notice that the Cape Fear River had what I would call moderately high TOC, you know, the 9 milligrams per liter. It's on the high side. It's not South Florida, but you know, it's on the high side, so it definitely will impact, again, both the absorption and the regeneration over a period of time. And is that the kind of work you're going to try and do over time? I imagine you're getting all kinds of ideas coming in, both from you and your students and other people, on things that you want to take a look at, and you have a limited bandwidth at your lab as to what you can do.
Yeah, right now there are many more interesting than we can physically do. You know, we also, you know, are evaluating a number of waters from around the country for uh, uh, the ability, their ability to remove PFASs by activated carbon. So we do these rapid small scale column tests. So one of our interests is, of course, to establish the factors that control PFAS removal by activated carbon. The background organic matter is the key factor. The type of activated carbon is a key factor. And then, of course, the structure of the PFAS themselves is an important factor. There's also a lot of interest these days in ion exchange as an alternative to carbon for PFASs, so that's something we're very interested in as well. So I guess one piece of advice, maybe unsolicited advice, is that we need to be very careful with data sets that have been obtained in groundwater and translate them directly to surface water when it comes to activated carbon absorption, especially with PFASs. The carbon performance is very, very strongly affected by both the concentration and the nature of the background organic matter, much more so than with other traditionally studied contaminants. So it's possible that a particular carbon in a particular groundwater works very, very well, and it may not work very well at all in a surface water.
All right, I got one more question from Mark, and then we'll try and wrap up and let you go, Detlef. Can you use GAC removal as a predictor of bioaccumulation potential, in particular compared to the legacy compounds like PFAS and PFOA? Is it unknown for these new PFAS?
So that's a question I have myself. I'm wondering whether carbon could serve as a model for that. I'm somewhat worried when I see high concentrations of things like the Nafion byproducts, or this there's 4 ether carboxylic acids in this stew that looks like it is very sticky. So I have concerns that some of these longer chain replacement compounds that we're finding and that are well removed by activated carbon are perhaps also quite bioaccumulative. Right now, the data are lacking, so I think it's an interesting hypothesis.
Yeah, I agree. It's something that's worth some investigation. So, Detlef, I really appreciate you taking the time today to talk to our members and government agency partners. If people have questions they'd like to answer, ask to Detlef, his email address is on this last slide. If anyone else has other questions about what might be happening with these compounds in Washington, D.C., feel free to send me an email at aroberson@aswa.org, and I'll do my best to answer this as these water policy issues unfold on the PFAS compound. So again, thanks, Detlef, and thanks to everyone for listening into this webinar this afternoon. Bye.
Great, thank you.